let's go back to the outline of what we're doing. We said that we want to have a new way to get the electric field. And the new way consists of two steps. The first step, if you know the charge distribution, how do you get the potential? The second step, if you know the potential, how do you get the electric field? We started with this step, the second step, and we defined the electric field in terms of potential this way. And now we're trying to address the question, what about how to get the charge distribution from the potential? How do we do this? I said before, also in a previous video, we're going to start by just looking at what the difference in potential is between two very close points. We already did this before. And then once we know that, we're going to be able to get the potential difference between 2 points that are actually any two arbitrary points. And then once we know that, we're going to be able to see how to get the potential at different points in space based on the particular charge distribution. So this is the steps that we're trying to follow. We're trying to do this step now, how to get the difference in potential between any two arbitrary points that are not necessarily very close to each other like it was in this case. So here we have our 2 points. We have point 1, we have point 2, and we want to get V2 minus V1, the potential at 2 minus the potential at 1. And we know that the potential difference between these 2 points has a fixed value. Remember, we said that if you add a constant to this point, let's say you add 5, and you add a constant 5 to this point, when you get the potential difference always stays the same. So the potential difference between 2 points always has the same value. So to get the potential difference, we need to think about the path that we're going to go from point 1 to point 2, because when you're in three-dimensional space, there isn't just one way to go from a point to another point in space. You can make any kind of path of any kind of shape going from the first point to the second point. So we want to introduce the concept of a path integral. A path integral, and we'll see what the relationship of this path integral is to the potential difference that we're trying to find. So the path integral, it's written as integration from 1 to 2 E dot dr, and let's see what this means. Integration means a summation. So what this integration does, it cuts up our path into small elements of length delta r. So this is delta r1, it's a vector that points from point 1 to this point, and delta r2 points from this point to this point, delta r3 points from here to here, delta r4 points from here to here, delta r5 points from here to here. Of course, there are not just 5 elements of length, there are an infinite number of elements of length, but I just drew 5 so you can see the problem. You can just see how it works. In principle, we should cut this up into an infinite number of parts. So what does this integration involve then? You get the value of the electric field vector at 1, E1, you take the dot product with delta R1, you get a number. Then you go to this element of length, you get the electric field vector at this point, E2, and you take the dot product with delta R2, you get a number. You take E3 dotted into delta R3, you get a number. You take E4, you take the dot product with delta R4, you get a number, and so on. And then this integral is basically the addition of all these numbers, the sum. So in the end, when you calculate this path integral from point 1 to point 2 along this particular path, in the end you're going to end up with a number, because you're adding this dot product plus this dot product plus this dot product plus this dot product plus this dot product, which gives you a number. So now let's see what the use of this is and what's the relationship of this to what we're talking about. We showed before that if this was our fundamental definition of the relation between electric field and potential, then the difference in potential between two very close points is minus E dot dr. We already did this before. So if you go to two points that are very, very close, this is what the difference in potential is. Now, if we take this intermediate result and now we integrate on both sides, if you integrate this from 1 to 2 and you integrate here from 1 to 2, integration of dv from 1 to 2 just gives you the potential at the final position minus the potential at the initial position. And so that's exactly what we wanted. We wanted to know how to get the potential difference between 2 points that are separated by an arbitrary distance or located at arbitrary locations. it turns out that the potential difference between 2 points is just the negative of this path integral that we just defined. So if you evaluate this integral, this path integral, choosing a different kind of path, will you get a different result for V2 minus V1? You won't get a different result. It turns out that because of the way the electric field is defined in terms of potential, actually, whichever path you take, it'll give you exactly the same result. And we just proved that mathematically just now. In the next video, we're going to give a more of an intuitive way to understand how this works. But for now, just note that the difference in potential between 2 points, when you evaluate it using this path integral, it doesn't matter which path you take at all. It won't change the answer at all. So the conclusion is, based on this fundamental definition relationship between potential and electric field, we've now obtained the integral form of this relation. By integrating, we got that the potential difference between 2 points is minus integration of E dot dr, and we've defined what an integral, a path integral is, and we've shown that it's independent of the path that you take. The difference in potential between 2 points is independent of the path that you choose between the 2 points. So as a summary again, this is the differential form of the relationship between electric field and potential, and this is the integral form. And basically the integral form says if you take any 2 points in space and you want to get the difference in potential between those 2 points in space, you need to choose a path. When you choose a path and you evaluate this integration and you multiply by -1, you'll get the difference in potential between the 2 points. And it turns out that this difference in potential doesn't depend actually on the particular path you choose. Whichever path you choose, you'll get the same result. Now, all this may sound a bit theoretical, so of course in the class you're going to be answering practical more examples, and also I'm going to put some examples right after this.